Okay, so what I'm going to be demonstrating here is three different ways to do a DC sweep analysis for this particular circuit. The first way is to use the DC sweep that is in the circuit simulator itself, and the next way is to use the oscilloscope that's in the circuit simulator itself, and then the third way is going to be to build this circuit onto a breadboard and use a real-world oscilloscope in order to take a look at that DC sweep type of analysis there. Okay, so first I'm going to do the DC sweep in the simulator, and so we're going to expect that out of this circuit, this is a half-wave rectifier, we're going to expect that throughout the sweep we're only going to see a positive voltage be distributed across this resistor. Now make sure that you do a little bit of analysis and make sure that you don't overload your circuit by choosing a resistor value that's too small here. This particular diode can handle up to like 200 milliamps of current, and I'm far away from that because 4 divided by 1 kilo ohm gives me 40 or 4 milliamps, which is far away from that. Plus, I also don't want to load down my signal generator in real life when I build this circuit. So I'm going to go ahead and do my DC sweep and have my setup with my start value at -4, my stop value at 4, and my increment at 1 millivolt, and then my output is going to be taken across this this probe here with respect to this probe with respect to ground, that is, and my source is going to be V1, which is this voltage source right here. So let's see what we get. And this is the curve that we get. This is what we would expect to see from a half-wave rectifier type of circuit. As we can see, we're all the way down here at -4, and then we terminate all the way here at 4, and this is the type of curve that you would expect to see because you don't get any negative voltage across that resistor. You're at 0, and then you only get positive voltage after this diode has been turned on. An ideal half-wave rectifier circuit would have no voltage drop across the diode, but you're dealing with, you know, a real-world diode, so of course you're going to have a voltage drop there that accounts for this, you know, this point where you're going to have to satisfy that as a threshold before it starts to move on and have some voltage distributed across the resistor, which is evidence that current is going through the resistor at that point. Okay, so that's our normal DC sweep. Next, I am going to do our oscilloscope version of this, and if I just leave the circuit set up as it is and open up an oscilloscope, then if I go to its normal mode, YT, and I just simply hit start, well, I have to change my mode here. That it ran DC sweep again. Change the interactive and then hit start. What do we get? Well, this is what we expect to see anyways. We expect to see that, you know, at 4 volts, where we're going to have, you know, channel A is my input, channel B is my output across that resistor, and we have 3.368 volts distributed across that resistor. We expect to see that because of our voltage drop across our diode when it's fully on, and that amount, the difference between 4 and 3.368, is going to be 0.632, and that's what it takes to turn on that diode. Okay. Now, if we go over to BA, which is operating this in a different way, in YT, the horizontal axis is time, the vertical axis is voltage, and it's displaying voltage for each one of these, the input and the output. But if you go to BA, then it's going to be totally different. It's going to be that the horizontal axis is actually the input voltage, and the vertical axis is going to be the output voltage, and then that's the way that you can get a DC sweep with it. But if I just simply run this analysis, I get nothing. That's because it needs to basically change. It needs to sweep somehow, and it's just the static voltage just sitting there at 4 volts, so we're not going to get anything, which is why I use this over here, which is a triangular voltage, and I have that set up so that my voltage amplitude is 8, my voltage offset is -4. That's because it's going to start at -4, and then -4 plus 8 is going to give me a +4. So this voltage amplitude is a peak-to-peak value, and if I offset it by -4, then it'll go up 4 and then come back down 4 with respect to 0. Okay, then the period, I just chose 20 milliseconds for that, and the fall time, I chose half of that, 10 milliseconds, so that automatically implies that the rise time is going to be 10 milliseconds, which is the same as the fall time, and so the fall time and the rise time is symmetrical, and that's what I'm going to be using for my triangular voltage setup. Then next, just to go over a couple of other things on the oscilloscope, I have it set to auto in the simulator version of the oscilloscope, and that's basically it for that. I mean, then I have my trigger with rising, and it's set to channel A, but I don't think that matters anyways. But that's my setup in case it does matter. And so I'm going to go ahead and hit run on this, and now we see that we get this curve. So see how you have that curve, and it updates itself. But once you get the curve up there, then you can just stop your simulation, and it'll retain the the result of that curve. So I have 2 volts per division. This way, this division is 2 volts. So starting here at 0, -2, -4. Starting here again at 0, +2, +4. And I also have 2 volts per division here as well. Now, one other thing with this, I'm going to use the cursors, but one thing with the cursors, channel A is my input, channel B is my output, but because channel B comes first, it reorders it on the cursor, and so the cursors see it a different way, and so it's using this, whatever's in this first spot here, it's labeled as channel B, but it's actually the first channel, channel A, and so basically it's more of like this is your horizontal axis, and this is your vertical axis, and that's the better way to interpret that. So as you can see, peaks at 3.368 at 4 volts. So that's what we expect to see, and that's what we have. Okay, so that all worked out good. Now next I am going to go into a real world measurement of this on a real oscilloscope. Okay, and so what I have here now is I have my oscilloscope and the circuit here. So what you want to do is you want to have a signal generator, and you want to set it up so that it goes through sweep mode. And when it goes through sweep mode, you're going to be sweeping through, you know, your entire voltage range, as I'm doing here right now. And this is still in YT mode, but this is how you have to set it up. This is how you have to go through your checks for your setup and see where you're at with this. So I'm going up and down from 4 to -4, and this is what you would expect on your oscilloscope here, because as you can see, the blue is the output of the circuit here. It's across that resistor, and it never goes negative, and it's always a little less than the input voltage, because that's the drop over that diode there. Okay, so that's what you expect there. Now, as far as the trigger is concerned, what I did with the trigger is I put the trigger down really low. I mean, the slope, I don't think it has to be anything else. Okay, so the slope doesn't have to be up and down. If it's down, let's see, it'll still trigger. But what I did with the trigger is I put it really low. I put it basically off the screen. And let me get out of this menu. Okay, so the trigger level is at like -5 volts. If I go too high with the trigger, I get some choppy sort of results there. See how it gets choppy? So you want to set your trigger up so that you're below your -4 volts, and you should be okay. It's even choppy there, so go even a little bit lower. I had it at -5 volts before. And so that works good there. So that's a check for how your trigger is set up. It's a check for how your circuit is set up with channel 1 and channel 2. And by the way, with channel 1 and channel 2, I am using some filters. That's how I have my filter set. It depends on how much noise you have. You may not have to use filters. It all depends. But I am using filters just to make that cleaner, because without the filter, it looks like that. And I could still do this procedure, but it's just going to be noisier looking. The line on the screen is just going to be really fuzzy and large looking, and I want a sharp line, so that's why I'm using filter. If I turn the filter off for channel 1, this is what that'll look like. I don't want it looking too fuzzy. Okay, so the next thing over is to go to your display menu. Now, your oscilloscope might be different, but in general, they all have, you know, some basic functions that are similar on them. And as far as run stop is concerned, it's in run mode. The trigger is on automatic, and so that's how it is set up. It's DC coupling, you know, just as we had in the simulator. DC coupling for channel 1, channel 2. And so that's all set up that way. Next, so I'm going to go back again to display, And originally I'm in my YT format. I'm going to switch from YT over to XY, and you see what we have going on there. Okay, so with this oscilloscope, what I'm going to need to do in order to retain the data from what it's acquiring from the circuit is I need to turn persist on, and you can put it on where it's infinite, and that's what I usually do. So put it on where it's infinite, get out of this menu here, let's see, it's menu escape, alright, and so that's what we have, and after a couple of iterations you'll see it, and that'll be that. One thing that I like about this is that you can actually look at some hysteresis. If your circuit has it, it'll show up as, you know, a separate line somewhere if it has some hysteresis to it, but obviously this circuit has no hysteresis to it. And so as far as cursors are concerned, on this oscilloscope, that function is not usable on this oscilloscope model, but regardless of that, we can still just take a look at what we have here. And so, you know, according to this, we're going a little bit below 4 volts. That's probably why I had to have the trigger set to like -5, because we're a little bit below -4 volts. And that's still okay, long as we cover the range. I wanted to make sure I covered the range. And over here, you know, 1 volt per division. I'm a little bit more than a positive 4 volts, but that's okay. At least I'm covering the entire range. And so what do we have here? Approximately, you know, it's 1 volt per division, approximately about 0.6 volts or 0.5 volts. I have that bend there, and that's what we're looking for. So that pretty much does it for this whole entire demonstration. The only thing other than that I wanted to point out is also that if I turn my filter off, I just want to demonstrate what that's going to look like. And you have to do it for both channels if you're going to turn it off, and it is symmetrical for both. So go to my filter for channel 2, turn that off as well, and that's what it looks like, and that's what I was talking about. It's going to be a large fuzzy sort of a looking trace, and if you're okay with that, then you can use that, but I like the sharper look. So I usually take my filters and I use them to mitigate the amount of noise in the signal. And then that's what you will get. So that completes the entire setup and test here for using your oscilloscope in real time, and a real oscilloscope in real time, in order to plot a voltage sweep, a DC sweep, or a voltage sweep. There's different ways to say the same thing, but it's also a voltage transfer characteristic curve, and so you can use your oscilloscope for that. You don't always just only have to use a simulator if you don't have access to that. And so that completes it for my demonstration. Oh, just one more other last thing. This horizontal knob, it controls the sampling rate, and if you lower the sampling rate, it's going to look like that, and it's going to take more time to build up. But if your sampling rate is higher, then of course it's going to sample at a higher rate, and you're going to receive the data in less time. So again, if you don't have a circuit simulator available, or you just want the a real world test of the voltage transfer characteristic of the circuit, because you're dealing with unideal components here, non-ideal components here, and even though the simulator may tell you one thing, really it's best to also check that in real life, because these are non-ideal components. There are tolerance ranges to them, and so it's also good to do this in real life with a real circuit on the oscilloscope. So all right, so that's it for this demonstration. Hopefully it was helpful. Thank you for watching, and have a nice day.